Of course, today is the 3rd, but this is where we left off way back last week. And the thing that I was drawing your attention to at that point was the fact that we want to make sure that we're using good notation for the distances. So we can either put, d equals or delta x equals, but you want to make sure that that doesn't get confused with any of the lines from your force diagram, both for you and for grading purposes. So we're told that work equals force times cosine theta times d, and I've told you that I have a fundamental distrust of authority, and even though every single source says work equals force cosine theta times d, I don't trust it, and I still check to make sure that in fact it is cosine theta. But in this case it sure is. So the work done on the vacuum would be equal to the 50 newtons of force times cosine of 30 times 3 meters. And I blew my sig figs there, but you'll have to forgive me. Well, you don't have to forgive me, but I'm not going to fix it. And I'm going to do this for myself, like I said, because of my fundamental lack of trust and authority. Sure enough, that's the component of the force that's doing the work, and sure enough, that would be times cosine of the resultant vector for work. So, okay, it checks out. I'm good. So let's get a raw number. Okay, so I've got this raw number. What are the units? Well, it looks to me like Newton meters, doesn't it? Interesting. We'll just leave that right there for now, because we're going to talk about that in a second. Well, it turns out there's a special unit that's composed of a Newton meter, and that's a joule. So work is done in joules. Energy is also measured in joules. So if we sig fig this, and I think we have 3 sig figs, we get 1.30 times 10 to the second joules of work being done on the vacuum cleaner. All of the 5A problems on 170 are assigned. I'm going to give you about 10 minutes. I'd like you to get through just 1 or 2 of them, and then we're going to talk a little bit about the 4B stuff. Okay? Pick up with kinetic energy. So this chapter is about work and energy, and they're related. How many of you did anything with kinetic energy in physical science? And remember it. Crickets. Little tiny crickets. You already, I hope, know that kinetic energy is energy in motion. We didn't watch the Columbia Space Shuttle disaster film. We watched the fractals instead. But moving objects have energy. You know that. Energy is just the ability to do work. How many of you have ever been worked on by a moving object? What would that require? Let's think that through. So what is work? Okay, good morning, people. We're all going to stand up. So a moving object has the ability to move another object. It's got energy, and it can translate that energy into work. Kinetic energy is the ability of a moving object to apply force and move something. This is where I should take you all bowling. Oh my gosh, I need to get bowling pins and a bowling ball for this room. What does work on the pins?
The ball.
The ball. Why does the ball do work on the pins? Because it's moving, because it has kinetic energy. So we've said energy is the ability to do work, and 1/2 mv squared equals the kinetic energy of an object. Kinetic energy is equal to 1/2 mv squared. So the question I have for you, looking at that equation, which piece of that is more critical, the mass or the velocity?
Velocity.
Oh yeah, wait. Okay, good. You saw that. Yeah, because it's squared. The NOVA film that we didn't get to watch, which I'll link on Classroom. Some of you might find it interesting anyway. It's about the space shuttle. I get these confused. 2 of them have blown up in my lifetime, and I always mix them up. I think it was Challenger that blew up in 2003.
The Challenger was the one.
Okay, no, it was Columbia then that blew up in Yeah, see, I've seen 2 of these happen now. Okay, so Columbia was the one that went in 2003. On the Columbia, do you know what caused the whole problem? No. So interestingly enough, and I will take a picture of this here chunk of styrofoam for posterity. Okay, something is wrong here. There. Okay. Chunk of styrofoam, very, very, very light. And when the space shuttle was taken, so the space shuttle obviously has heavy-duty insulation underneath all those beautiful tiles that protect it, because as it comes back into the atmosphere, it heats up ferociously due to drag, which we talked about in Chapter 4. As it hits the atmosphere, air resistance increases, and the whole thing basically gets frictional heating. And if it wasn't protected somehow, it would all just burn up. Oh, well, there's a bit of foreshadowing. So it's got styrofoam insulation on the fuel tank so that they don't ice up, and then the entire craft is covered in heat-resistant tiles. And if you look at their ceramic, and they honestly look like roof tiles. They're kind of overlapped so nothing can get in. And what they found was that when it took off, a chunk of styrofoam came off the top, bounced down. You see it in the video glance off the wing. And then it went into space. It's a chunk of styrofoam. Weighs nothing. Weighs absolutely nothing. And it was observed on takeoff that this chunk of styrofoam had hit the wing, hit the leading edge of the wing. And you could see there was a little sort of spray of material, but they didn't really know what it was. And the engineers on the project were told, and there's a great interview, I will link the video because it's worth a watch. We're told, tell us if there's a risk. And they said, well, can we get somebody out to do a spacewalk to actually examine the wing? No, just tell us if there's a risk. And the engineer said, it's akin to being told, you hear a car accident from inside your office out on the street, and you're told, do we need to call an ambulance? Well, I don't know. Let me go look. No. You can't look. Just stay there. Do we need an ambulance? Well, I don't know. Let me go look. No. You have to stay right there. So they didn't examine it, but the leading sort of feeling was, it's a chunk of styrofoam, for God's sakes. It couldn't do any damage. Look at this stuff. This could not damage the space shuttle. Come on. And that same engineer later in the movie says, and this is why I've showed it sometimes, it's basic high school physics, KE equals 1/2 mv squared. It's not the mass that matters. It's the velocity. And of course that little tiny piece of styrofoam, and it was literally a chunk about that size. It was not a large chunk of styrofoam, so there was very little mass to it. But when, after the fact, after the whole thing broke up, heated up, and if you don't know, what happened was the ceramic heat tiles were damaged, allowing hot gases to get under the rest of the tiles, and then the body of the ship started to heat up, and then the whole thing disintegrated and everybody died. And it broke up in a stream of debris, basically from California across Texas, and chunks of the space shuttle were found in a long pathway, and that's how they reconstructed what happened. When they went back after the fact and looked at the velocity at which that chunk of styrofoam would have been traveling, you can calculate the amount of work that piece of styrofoam is capable of doing, and it was horrendous. So I'll link the video. It's well worth a watch. Yeah, mass is not the critical piece. It's really how fast you're moving. That's where you really get the energy from, is the speed. This is also why, and having just traveled the Pennsylvania Turnpike over the weekend, the big signs you see in construction zones, and I don't travel the Ohio Turnpike much anymore. In PA right now they've got a campaign that shows pictures of actual turnpike highway workers in their little orange vests, and it says, at 45 miles an hour, if you hit me at 45, you'll break my bones. If you hit me at 65, you will kill me. It's all about velocity. Speed is a much bigger determinant of damage in an accident than the mass of the vehicle. Now, that said, you'd still rather be hit by a Miata than an Expedition, but you can actually look at how fast the Expedition and the Miata would have to be going to do the same amount of damage. And it's pretty interesting calculation, derivation. Sorry, I know. Okay, so I'm going to shrink this and we're going to do this together because it makes much more sense this way. So if you've got an object with a mass that is moving on some frictionless plane, when a force is applied to it, it gets an acceleration. So we're going to use the not entirely frictionless plane of my desk and this calculator. When I apply a force to the object, it moves. It's then got an acceleration. So we know that whatever force was applied equals its mass times acceleration. And whatever work has been done on it is equal to, and we're going to leave out the cosine for right now, we're just going to note that this is on the axis of the displacement, delta x. Okay? You probably want to write this derivation down. It becomes really important. So we can do a substitution and put this ma in here. So now we have work equals mass acceleration delta x. Cool. And note this, a delta x. I'm going to shrink that. So you might recall that Vf squared equals Vi squared plus 2a delta x. Oh, hey, look at that. Huh. Interesting. Interesting. We can solve this for a delta x. Oops, equals. So Vf squared minus Vi squared equals 2a delta x. So divide them both by 2, we've got that. So now, looky here. Oh, how cool is that? We have this that we can plug in there. Huh. So work equals mass times Vf squared minus Vi squared divided by 2. Huh. Interesting. Interesting. Well, let's go ahead and we'll do a little bit of distribution here. I'm going to go back to red. I'm going to shrink this, since that was just my so now, whoops, what we've got is W equals mass Vf squared minus mass Vi squared divided by 2. Shrink that. Well, the work done is equal to 1/2 the mass times final velocity squared minus 1/2 the mass times the initial velocity squared. Does this start to look suspiciously familiar? What does it look like? Talk at your table. That's weird. Ke equals 1/2 mass velocity squared? Huh. So then, interestingly enough, if we're talking about the final velocity and the initial velocity, we're talking about that change in velocity, that would be, oh yeah, the change in velocity. So this is the final Ke, and this is the initial Ke. Oh. So, the net work done on an object is equal to 1/2 its mass times, whoops, its final velocity squared minus 1/2 its mass times its initial velocity squared. In other words, the net work is equal to KE final minus KE initial. So the net work is equal to delta KE. Oh. Now, what you're going to do, because you also know that net work equals F cosine theta d. Do you see what's coming? Substitutions. This is where we start to build the calculations that are needed to throw your bungee jumper off the cliff. So you'll be getting your bungee jumpers later this week. I have to go to Aldi's and buy the bungee jumpers that you can name before you throw them off the cliff. Let's do a problem. Moving at 3 meters per second, how much kinetic energy does the bowling ball have? How fast does a 2.45 gram table tennis ball have to move to have the same kinetic energy as the bowling ball? Is this speed reasonable? So we're going to start off. We have mass of the bowling ball, 7.00 kilograms. Mass of the tennis ball, table tennis ball, 2.45 grams, which is, well, let's just do this the easy way. 2.45 times 10 to the negative third kilograms. And the velocity of the bowling ball is 3.00 meters per second. Okay, so what we want to know is the kinetic energy of the bowling ball, which is equal to 1/2 its mass times its velocity squared. KE of the bowling ball equals 1/2, 7.00 kilograms. Times 3.00 meters per second. Let's get a raw number. We got the first part. We know what the kinetic energy of the bowling ball is. Now, with the little tiny mass of a ping pong ball, how fast would it have to be going to have the same kinetic energy? So we've got our solve there. Shrink that. I'm going to move all this up and shrink it. So square root of 2 times 31.5 joules divided by 2.45 times 10 to the negative third kilograms equals the needed velocity. Let's get a raw. We get a raw number of over 160 meters per second. Probably not a reasonable velocity to achieve with a ping pong ball. Now, if it's coming off the space shuttle, you could probably get that, but it's probably not coming off the space shuttle when you hit it across the table or roll it down the alley. 4B, all of them are assigned, or 5B, good Lord. Let's not forget that that's done. So 5B starts on page, it's 174. Okay, because I jumped the gun. I should have stopped before we did work kinetic energy theorem. Okay, get working. You can probably get 1 or 2 of those done. They're really, really easy.